Hi friends, today I shall be introducing you to another simple but a very useful and widely used data structure, the queue. A queue is simply a waiting line that grows by adding elements to its end and shrinks by removing elements from the front. Compared to stack, it reflects the more commonly used maxim in real world, namely first come first served. Waiting lines in supermarkets, banks, food counters are common examples of queues. A formal definition of queue as a data structure is: a queue is an ordered homogeneous collection of elements in which elements are appended at one end called the rear end and elements are deleted at the other end called the front end. Just like the queue of real world, the data that goes first into the queue is the first one to be retrieved. For example, consider people in line on a library counter. As people arrive, they enter at the rear end of the line and they are served in order from the front of the line. The first element inserted into the queue is the first element to be removed. For this reason, a queue is sometimes called a first in first out data structure as compared to stack, which is a last in first out data structure. We now have a look at the basic queue operations. Like stacks, there are two basic operations that can be performed on a queue. Enqueue, this operation inserts or adds data in the queue. The data will be added to the rear of the queue. Second operation is dequeue. This operation removes the data which has been in the queue for the longest time. The data is present in the front of the queue. Now we look at implementation of the queues. There are many possible ways to implement the queues. Queues can be implemented using an array with front at index 0, an array with floating front and rear, a circular array with floating front and rear which wrap around, a singly linked list with front, a singly linked list with front and rear, a doubly linked list. Today we shall see how queues can be implemented using arrays. The complete implementation needs to maintain two pieces of information. First is an array to store the queue elements. Secondly, the indices of the front and rear elements in the array. Queues can be implemented using arrays by three schemes. In the first scheme, the value of front is fixed at index 0. This is a very simple but inefficient scheme in which the elements of array are forced to lie in positions 0 to position size minus 1, where size is the number of elements currently in the queue. The front is implicitly index 0 and rear is size minus 1. When we remove an element, we would remove it from position 0, and when we add an element, we would add it at position size and then decrement size. Adding an element can be done in only a few operations. The inefficiency comes when we remove an element. We remove an element from position 0, so when we remove, we have to shift the remaining elements from positions 1 to size minus 1 by 1 position. So, they would go from positions 0 to size minus 2 as shown in this slide. This way of removing requires size operations, which is clearly undesirable if size is big. Thus, we reject this solution because it is too expensive to move everything down every time we remove an element. In the second scheme, the entries of queue are not moved. Instead of keeping front as 0, we make it mobile and keep track of its position. Each time an element is deleted, front is incremented to next position. Similarly, each time a new element is inserted, rear is incremented by 1 and the element is inserted there. As shown in the slide, consider a queue with capacity for 6 elements. The current values of front and rear are 0 and 3 respectively. When an element k is inserted in the queue, rear is increased by 1 and the new element is stored at that location. When an element is deleted from this queue, front is increased by 1 and it points to element at index 0. Again, when new element is inserted, rear is increased by 1 and it becomes 5 and new element is inserted at that location. But there is a problem with this implementation too. We have now reached the end of the storage. Even though one slot is free, but we still cannot insert another element as rear has reached the highest index in the array. So, this is the disadvantage of this scheme, that if rear has reached the maximum index and even there is no element in the queue, we still cannot insert a new element. So, we have to look at some other alternative implementation which does not suffer from this disadvantage. The third implementation of queues uses a circular arrays. As queues implemented as linear arrays have the drawback that once the queue is full, even though we delete a few elements from the front and relieve some occupied space, we are not able to add any more elements as the rear has already reached the queue's highest position. The solution lies in a queue in which the moment rear reaches the highest index in the array, the first element will become the new rear of the queue. Both the front and the rear pointers wrap round to the beginning of the array. Such queues are called circular queues. Circular queues are better than normal queues as they effectively use the memory space. Initially, when a circular queue is empty, the front and rear values are 0 and -1 respectively, and the queue has a null value for all its elements. Every time we add an element to the queue, the rear value is incremented by 1 till the time it reaches the upper limit of queue, after which it starts all over again from 0. Similarly, every time we delete an element from the queue, the front value is incremented by 1 till the time it reaches the upper limit of queue, after which it starts all over again from 0. As for example, consider this circular queue. The queue has space for 8 elements and 6 elements are present in the queue. The values of front and rear are 0 and 5 respectively, which means that the next element to be deleted will be the element stored at index 0 and new element will be stored at index 6. The state of the queue after following sequence of operations dq, nq6, dq, nq52, nq63, nq29 is as shown in the slide. In the linear implementation, the queue is full when rear reaches the highest index of the array, but in circular implementation the rear again starts from beginning after reaching the highest index. So, how we come to know that the queue is full? As example, front is 3 and rear is 2 and the queue is full. So, we can say that in circular array the queue is full when front is equal to rear plus 1. Next, now if we start deleting the elements one by one, the state of queue in different stages is when all the elements have been deleted, state of the queue is, as we can see front is 3 and rear is 2. So, front is rear plus 1, and interestingly when the queue is full, then also front is rear plus 1. So, how do we come to know if the queue is full or empty, since for both cases front is rear plus 1? A possible solution is to keep an extra variable count for keeping track of number of elements in queue. Initially count will be 0, and when an element is inserted in the queue, count is incremented by 1, and when an element is removed from the queue, count is decremented by 1. When count equals the maximum size of the queue is full, and when count is 0, the queue is empty. Thus, the complete implementation of circular queues will maintain the following information. First, an array to store the queue elements. Second, the indices of the front and rear elements in the array. Third, count of number of elements in the queue. The complete implementation of circular queues using the above concepts is as follows. The structure used to implement the queue is as follow. Next we see how the basic operations NQ and DQ will be implemented. These functions will be needing 3 supporting functions which are implemented as shown in the slides. The function init is defined to initialize the queue. Initialization of queue is quite simple. We just set the value of the variables front and count to 0, while rear is set to -1. The function empty checks if the queue is empty by examining the value of count. If count is 0, then the queue is empty. The function full checks if the queue is full by examining the value of count. If rear equals maximum index of array storing the queue, then function returns true. The function NQ inserts a character X into the queue. Before adding the item to the queue, the variable rear is incremented by 1 and the resultant values modulus of max q is taken. As a result, if rear equals to max q, it is reset to 0. X is then inserted at array index rear. Also, the variable count is incremented by 1. The function DQ retrieves the element at the front of the queue and stores it in the variable C. Front is then incremented by 1, and in case it becomes equal to max q, it is set to 0. This is achieved by taking modulus of max q. The count variable is then decremented by 1. At the end, the function returns the value stored in variable C. We conclude our today's lecture by having a look at animation of circular queues available at the following URL. So, with this we come to the end of today's lecture. Today we had introduced the queue data structure. Queue, as we have seen, is a linear data structure in which data can be added to one end and retrieved from the other. Just like the queue of the real world, the data that goes first into the queue is the first one to be retrieved. That is why queues are sometimes called as first in first out data structure. Queues can be implemented both using arrays as well as linked lists. Today we discussed the 3 implementations of queues using arrays and found that the most suitable implementation using arrays was the circular queues implemented using floating rear and front ends. In the next lecture, we shall be discussing the applications of queues in detail. Thank you. you.